Hello, everyone. So I know I'm giving the closing keynote at a software conference, one of the great software conferences, RailsConf. And normally I'm used to being kind of in person, and I could kind of gauge a room and gauge some body language. But my guess is, looking out over the virtual room, that most folks have not done a whole lot with hardware in their careers. That I assume we've got a lot of software engineers. Certainly, I'm a software engineer. And, kind of depending on when you came up, we have gotten further and further and further away from the hardware. Or so I would have thought, actually, before that little spot we had from the sponsor, where they talked about actually deploying on ARM, which was really interesting. So I think the subject of my talk today is on hardware software co-design and what I see as a coming golden age. And as I said, there has been this divide where we in software have grown further and further apart from the underlying hardware. And on the one hand, this is really important in that we have been able to be disconnected from the hardware, and we've been able to focus on pure software architectures, because hardware can be a pain in the butt. And if you are of my vintage, if you came up in the 90s or earlier, you probably have stories of racking and stacking servers and cabling and everything else and dealing with different vendors. And you might think to yourself, boy, I'm really happy I'm not back in that time. I'm glad I can just provision on a cloud somewhere. And that's great. That is all very important. But there is a risk there. And that risk is that we take this software-centric thinking too far, that we begin to think that only software matters, that the hardware vessel that we're actually operating on is irrelevant, or worse, that it is something to be denigrated or dismissed, and so on. And I'm here to tell you that thinking is really problematic. That software centrism can be really problematic. And I hate to kind of throw him under the bus here, but I think that really is epitomized by Mark Andreessen's 2011 essay, "Why Software is Eating the World." Now, I got to confess, I've got a complicated relationship with this essay. So this essay was originally published in 2011. When it was originally published, I kind of thought it was dumb, in that I thought a lot of the things that it was saying were either obvious truisms or things that were obviously not going to happen. And 5 years later, I looked back on it and I thought, well, maybe I was too quick to judge, and maybe that essay was more prescient than I gave it credit for. And in particular, this is a line that I've quoted in the past, many people have quoted, and this line feels prescient, where Andreessen talks about software companies that are going to disrupt the larger world. And certainly after, I remember I gave a keynote on the morning after the election in 2016, and really reflecting back on this essay and wondering about its prescience. And that is true, but only to a degree, really. It is true that yes, the taxi companies have been disrupted by a software company, and yes, the hotel companies have been disrupted by a software company, but not thoroughly, not completely. And that's not the whole story. So there's more going on than that, and there's a lot in this essay that has not come to fruition. So I want to talk about that a little bit. But before we do, there's one note that definitely rings true, and maybe the truest note in this whole essay is where Andreessen reflects back on his experience at LoudCloud and looks at, now it's 2011, it's 10 years ago, and realizing that a service that cost 150 grand a month then could be stood up in AWS for $1,500 a month. And that is unquestionably good, right? That's correct, accurate, good, and so on. So this part of the essay is just like spot on. This is a truism. We'll talk about why this is true. There's a lot that is involved in getting that $150,000 down to $1,500. It's Moore's Law, it's open source, and then it's the public cloud, of course. But this is where it really overshoots. Where it overshoots is where it believes that software and software alone is going to disrupt arbitrary elements of the economy. And this is where it becomes really, I think, implicitly dismissive of the complexity of these systems. So in particular, he talks about healthcare and education. So healthcare and education, in my view, are next up for fundamental software-based transformation. My venture capital firm, A16Z, Andreessen Horowitz, is backing aggressive startups in both of these gigantic and critical industries. We believe that both of these industries, which historically have been highly resistant to entrepreneurial change, are primed for tipping by great new software-centric entrepreneurs. Okay, out of curiosity, what are these software-centric entrepreneurs that have disrupted healthcare and education in the last decade? Because I'm not sure that I really see it. And in fact, if you kind of think about those two things, healthcare and education, what are the most important innovations in healthcare and education over the past decade? I think for healthcare, you're going to be very hard pressed to argue that it's not mRNA-based vaccines as the most important innovation. Certainly, I'm looking forward to getting my mRNA-based vaccine. I assume many of you already have it or are waiting to get your vaccine. It's hard to argue that that's not exactly software-centric entrepreneurism that gave us that, right? That is, now clearly, software played a very large role in that. But it is overstating software's role to say that software alone has actually delivered that healthcare innovation. And education is actually even more interesting in my view, because what is the most important change in education in the last decade? I'm not sure how many of you have kids. I've got 3. All of them have been told not to interrupt me during this keynote, so we'll see if one of them comes in during the middle of it. But my kids, like your kids probably, have been at home for the last year, and they've been distance learning because of the pandemic. And what have they been distance learning on? They have been, if your kids are like my kids, and they're like 60% of all school-age kids, they're on a Chromebook. I would argue that the Chromebook is one of the most important innovations in education. And I know it feels mundane that the Chromebook is so important, but the Chromebook actually is, and why is the Chromebook interesting? At least interesting to me, the Chromebook is hardware and software together. It is an integrated yet open innovation. It's secure. If you've dealt with a school district at all, you know the ability to administer many Chromebooks is part of what makes it appealing for schools. It's low cost. It's got a lot of advantages. And those advantages are due to hardware-based innovation. And that is actually the big problem with Andreessen's Software's Eating the World piece. It misses hardware entirely. And that's not to say that hardware it dominates software, that software is unimportant. It's just that hardware and software are important. You cannot dismiss hardware. You cannot dismiss software from hardware entirely. And you have to look at the way these two very important elements of a system interact with one another and deliver innovation together. And indeed, if you look at the companies that Andreessen calls out as really thriving, and he calls them all software companies. He calls Amazon a software company and Google a software company. And it's true that Amazon, obviously software plays a very important role at Amazon. Software plays a very important role at Google, but it is overstating the importance of software to call them purely software companies. Both of those companies have very significant hardware components that you cannot take away and still have the same company. They could not be all software-based companies in the case of Amazon and Google. It's in part because they are the public clouds. But even beyond the public cloud, there are significant hardware components to what those companies have delivered, whether it's the phone, whether that's an Echo or an Alexa. There are lots of other surround that is hardware and software together. And indeed, if you go back to that essay and you look at the software companies that Andreessen calls out as the real model for the coming future, what are they? Zynga, Rovio, Groupon, Living Social, and Foursquare. So I don't know. I'm sure some of you count at least one of those companies in your past resume. You probably don't work there anymore. All of those companies are a shadow of their former selves. They are pure software companies, but they have come and largely gone. They've largely disappointed. And Andreessen ignores, he's actually dismissive of Apple. Apple is up a factor of 15 since that essay was written in 2011. And it entirely ignores companies like NVIDIA. NVIDIA is up 57x, AMD up 14x, or even Intel. Even Intel, your money would be better off in Intel than any of Zynga, Rovio, Groupon, Living Social, or Foursquare. And indeed, your money would be much better off in Apple, NVIDIA, or AMD than it would be being an LP for A16Z, their venture capital firm. Not to put too sharp a point on it, but I think that we overstate the importance of software. And that's a mistake. That's arrogant of us as software engineers. We should appreciate that software plays a very important role, but not an exclusive role. And hardware itself plays a very important role in our ability to innovate. So, and I mean, again, not to put too sharp a point on it, it's unlike me to put a meme on a slide, but I just couldn't resist in this case. Actually, it's funny, this meme, which I love, I feel it's apropos here. I don't know if I'm going to start using memes on slides now, but I feel it definitely fits here. This meme, I wondered how old this thing was. This is just shows you how much the pandemic has distorted time and space. This meme, you may guess, like, how old do you think this meme is? I don't know. Like, does that date from like some video game from the 90s or something? I don't know. This meme is created in June of 2020. So I don't know, maybe you're not surprised by that. I was very surprised by that. I think time is kind of swirling by here and taking both too long and not long enough. Anyway, but the software does run on hardware, and it always has. And for that, let's actually turn the way back dial. Let's go to a different essay. One that is another famous essay, cramming more components onto integrated circuits. And you may recognize this one. This is from Gordon Moore. And this essay is unbelievable. This is the essay where we get Moore's law. And this essay is just crazily prescient. So this is 1965. This is older than I am. I would dare say it's probably older than many, if not most of you. So this is a long, long time ago. And yet Gordon Moore talks about the future of integrated electronics is the future of electronics itself. And then he says, this is amazing to me, integrated circuits will lead to such wonders as home computers. And actually, he must have written home computers, been like, no, that actually sounds totally crazy. That sounds completely bonkers. Let me at least I'm gonna take half a step back from home computers and dial that back to, okay, terminals connected to a central computer. Clearly, I did not mean home computers. That's obviously nuts. Automatic controls for automobiles and personal portable communications equipment. It's like, okay, I got my personal portable communications equipment. I got my automobile out front that is loaded with ECUs. And of course, I'm on my own home computer, or at least a terminal connected to a central computer known as the internet. It's amazing to me that this in 1965, Gordon Moore could see that this coming dawn, this new age that was going to happen, because what did Gordon Moore see? Gordon Moore saw that we were getting denser and denser and denser with respect to the transistors on an integrated circuit. And he saw that we were going to see all sorts of advantages. And as he says, that the principal advantage is going to be lower costs and greatly simplified design. So he sees that the cost of these things is going to come way, way, way down. And that's what's going to allow all of these new applications that Gordon Moore, can see in 1965 somehow. I think I just kind of throw this one in there because it's kind of interesting that the gallium arsenide has always been very popular as a potential semiconductor. What's interesting is he says silicon is likely to remain the basic material, and boy, it sure has. So Gordon Moore just cannot miss in this piece. And the thing that is, he also points out that's interesting is looking at the actual cost over the lifetime of a generation and realizing that as we add more and more and more components, we do get to the point where decreased yields will limit the benefit. So we hit, for any given generation, there's a sweet spot where we get the right number of components on the IC, the integrated circuit. And he kind of graphs this out, looking from 62 to 65, and then forecasting into 1970. And you might say, well, is this Moore's law? Is Moore's law that the cost per component drops exponentially over time? It's actually not Moore's law, or not what we come to think of Moore's law, but it might as well it could be, because this is what he talks about in this paper, is this drop in cost over time. And of course, this would continue over time. You may also, it's when he talks with the actual numbers, he forecasts that by 1975, we are going to have the number of components, transistors per IC at minimum cost, that is that lowest point of the curve, will be 65,000. And I believe that a large circuit can be built on a single wafer. It's just amazing. And this is where we get to what we more commonly think of as Moore's Law. We more commonly think of Moore's Law as the doubling of transistor density over time. So the number of transistors we can fit in a unit area over time. And this has been remarkably true, that if you take the log plot of this, it's been remarkably linear up until when it broke down. So we'll talk a little bit about when Moore's Law broke down. The one thing I also want to point out, just because it's amazing, is the when we actually are able to get more and more components on this thing, he believes we don't actually need, we can use existing optical techniques. We don't need to go to more exotic lithography, which he was right on. That didn't happen until much later. And then he says, and I'm not sure to what degree this was kind of common knowledge at the time, but he points out that shrinking the putting more and more transistors on an integrated circuit allows it to operate at not just lower power, but also higher speed. So if you have the same power, it actually operates faster. And this is actually what we would come to know as Dennard scaling, that the clock rate would go up over time. Again, I'm not sure how commonly it was known, but he just kind of says this casually in this amazing paper that says that forecasts so much of the future. So the thing that's also funny about that 1965 paper is he doesn't actually talk about Moore's Law per se. He just makes a bunch of outrageously prescient and astute observations. He doesn't actually call out any of them as a law. He just says, like, wow, this seems to be true. It seems to be holding. The term Moore's Law actually was coined later by Carver Mead. Carver Mead of VLSI fame, absolute giant of VLSI, in 1971, as he was beginning to try to determine what the ultimate physical limits are. How dense could we actually make a CPU? And Moore himself did update the law in 1975 at this point in time. He is calling it Moore's Law himself to be the doubling of transistor density every 2 years. And then Dennard scaling was also outlined. So Dennard scaling is this idea that as we make these things denser, they become faster. So for many years, and when I was growing up, Moore's Law could reasonably be inferred to be the doublings of transistor density, speed, and economics. Things got denser, they got faster, and they got cheaper. And this is just bonkers. And if you are not of my vintage, let me tell you the stories of the good old days of Moore's Law. It was crazy during the 80s and 90s when there would be a computer that would come out, and your computer that you bought a year and a half ago would be obsolete. A computer would have come out that is twice as fast as the computer you bought only a year and a half ago. And this is on very vivid display with the turbo button. Now, I'm sure that unfortunately, I can't see you all, but I assume that some fraction of you are kind of nodding along with like, oh my God, the turbo button. And some other, perhaps much larger fraction of you are thinking, what the hell is the turbo button? The turbo button was a button they added to solve a problem. The problem was that we are making these things so much faster that the games that have a timing loop based on the number of cycles are now unplayable on the faster machine. So you had a 4.77 megahertz PC XT, and you're now running it on an 8 megahertz PC AT, and the game is now twice as fast and is unplayable. So how do you solve this problem? Well, instead of, they wanted to add a button, effectively a button to slow the computer down. And you can just imagine engineers having the reaction of like, oh my God, we're gonna add a button to slow it down? Like what do you call it, the go slow button? Well, some marketing genius, to the best of my knowledge, unnamed, but maybe we can figure out who he or she was, figured out that like, no, we're not going to add a button to go slow. We're going to make a button to go fast, and it's going to be on by default. So that is truly an act of marketing genius. And we had the turbo button. That turbo button was on by default. And if you wanted to play your old XT game, you would undepress the turbo button, and it would go slow effectively. And it was, but we needed that. And we needed that because that's how disruptive Moore's Law was. Moore's Law was so disruptive, it was literally running software too quickly. So that was amazing, kind of those 80s and 90s. But even as we got into the mid 90s, we actually were having the CPU was actually going too fast relative to memory. Memory was not getting any faster. CPU was getting a lot faster. Memory was not getting faster. And more workloads began hitting what's called the memory wall. And the memory wall means they were blocked on memory all of the time. So you had the CPU was effectively doing a load and waiting for hundreds of cycles for that load to return. And if it was chasing a pointer and kind of a systems workload, it would immediately turn around and do another load. And that load, if it missed in the cache, would again spend hundreds of cycles. And caching was certainly necessary, but it was also insufficient. Actually, a funny story about caching. Just a quick aside, people may not realize, caching invented in the IBM, this System 360 Model 85 back in the 60s. And the engineers that came up with it, I came up with the idea of a cache. They actually didn't come up with the name. What they came up with was like, well, it's a memory buffer, so it's a muffer. And they went to go publish this in the IBM Systems Journal. I'm like, hey, we want to talk about muffers. And great credit to the editor of the journal who's like, hey, this seems like a very important, profound idea. I don't know about muffer, though. Muffer is not really doing it for me. Like, what? Could we work with you on a name? And they kind of went back and forth. He's like, well, it feels to me like you're kind of putting something there and getting it later. And that reminds me of like a cache, like a food cache or a weapons cache. And they agreed that caching was a better name. But we could be calling this muffering today. So thank God for that editor of the IBM Systems Journal. But so caching was great. Caching allowed us to work around the memory wall to a large degree, but it wasn't entirely sufficient. And as we hit the mid to late 90s, we needed to do more. And so one of the things that we did is we added more CPUs to the box. We called symmetric multiprocessing. So we're now going to have multiple compute elements. And so we can better assure that the system can make progress, which is great. The reason I came to Sun in 1996 was because Sun believed emphatically in symmetric multiprocessing. Sun bet the company on symmetric multiprocessing. If the symmetric multiprocessing had not worked, Sun would have perished even earlier. SMP was a huge part of my upbringing. It's great, it's important, but it also does nothing for single thread performance. So in that late 90s, early 2000s, there are lots of different ideas on how to make a single thread of execution faster. You can do very deep pipelining, but deep pipelining was proving to be problematic. You can do something called VLIW, very long instruction word. As they say, you haven't heard of it for a reason. Interesting idea, also basically a failed experiment. So what we, and by we, I really mean Intel, really got the charge on this, is what Intel really realized is like, actually, we can be much more rampantly speculative about the things you're going to go execute. So you've got a program, and this could easily be a program in Ruby or in any language that is effectively doing a lot of loads through memory, and it's loading objects, and then from that load, it's going to perform another load, and so on. It would speculatively load things that you're not necessarily going to load to get that happening in the background. So it would hide that latency. And by the time you issued the load, hey, here it is. It's sitting in cache for you. And that seemed great. Of course, now is when we should like cue the ominous foreshadowing music, because that speculative execution would come back to haunt us in our annus horribilis of 2018 with Spectre and Meltdown, where the rampant speculative execution actually served to undermine the security of the microprocessor. But that would be many years in the future. All of this serves to point out that scaling, even when Moore's Law was at its height, at its heyday, Moore's Law still posed a challenge because DRAM wasn't getting any faster. In about 2006 and kind of the first decade of the 2000s, Dennard scaling ended. And if you kind of came up at that time, maybe you had a 1 gigahertz machine and thought you'd one day have a 10 gigahertz machine. Well, you don't. And you don't because we can't really make a 10 gigahertz machine, not one that's practical anyway. So Dennard scaling ended largely due to current leakage. And by then it was clear, in part because of the success of SMP, symmetric multiprocessing, that what we actually want to go do is take many, many cores and put them on a die. We want to have chip multiprocessing. And because of all the software work that we all had collectively done in the operating systems, the databases, the languages, and so on, we were ready for chip multiprocessing. And that ended up clearly being the trajectory. And that's what we've done ever since. So since this time, 2006, we've continued to increase transistor density, but we have those transistors go to multiple cores. So when you buy even a laptop computer, it has many, many cores on that die, and you can light them up in parallel. Now, that's great, but it's also a challenge because you can't actually light up an entire core for reasons of in terms of actually lighting up the entire thing would potentially brown yourself out. So there are still challenges about how you can actually light up that whole core and draw power. And since then, what we have seen is that Moore's law has decelerated. Since the end of Dennard scaling, Moore's law went on for another couple of years, but it is slowed down. That certainly in 2018, GlobalFoundries pulled out of their 7 nanometer development. That has basically left TSMC and Samsung and Intel as the world's foundries. TSMC and Samsung on 7 nanometer, Intel really struggling on 14 nanometer. Intel had a project called Cannon Lake, which is a total disaster, unmitigated disaster where they attempted to move to a new fabrication process. I look forward to, it sounds like a Hardy Boys mystery, but I want to read like the conflagration at Cannon Lake about whatever the disaster was at Cannon Lake. Cannon Lake never actually really meaningfully shipped. They ship only in very small quantities. So Intel was trying hard to get to a denser process. They were unable to get there. TSMC was able to get there, but it was very expensive. It was very expensive to everybody. And moving to yet a more dense process in 3 nanometer and 5 nanometer requires us to move to new technologies. FinFETs and GAFETs these are FIN field effect transistors and gate-all-around field effect transistors, effectively new technologies to be able to cram in yet more transistors into a smaller unit area, but it's very expensive. It requires us to rethink a bunch of things. And it requires EUV photolith, extreme ultraviolet photolithography. So these are really, really expensive. Now, you may wonder, you're like, okay, wait a minute, I'm at a software conference. What are we talking about here? And you may well wonder, when we say 7 nanometer and 5 nanometer, what is 7 nanometers? I mean, I know how long it is, like it's not very long, and 5 nanometers is even shorter. But when we talk about a process node being 7 nanometers or a process node being 10 nanometers or 22 nanometers, what are we actually measuring? And hey, by the way, like, I'm just a software person, but how big is a silicon atom anyway? Like, aren't we getting kind of close to a silicon atom? And the answer to that second question is yes, we're definitely getting close to a silicon atom. A silicon atom is only 210 picometers. And from the van der Waals radius of a silicon atom is 210 picometers. So you can't get to silicon atoms any closer than 210 picometers. So it would seem that like, wow, isn't 3 nanometers, isn't that a problem? Isn't that like 15 silicon atoms? It's like, well, it would be if we were actually measuring anything with nanometers, but don't worry, we're not. And this is just, I think, terrible. The process node names measure actually nothing. There is nothing that is actually 7 nanometers or 5 nanometers or 20 nanometers or 22 nanometers or 40 nanometers or 90 nanometers. It has been a long, long time since that metric meant anything. It doesn't actually measure anything. What it does do is it expresses loosely density. So a 7 nanometer process will generally have much higher density than, say, a 14 nanometer process. But it depends. And Intel, famously, Intel's 10 nanometer process yields about the same transistor density as TSMC's 7 nanometer process. It's like, oh God, what means anything? So it's very frustrating. And you have to kind of treat this directionally. But don't treat this as a physical limit. What you want to actually look at is the number of transistors per unit area. So 7 nanometers is about 100 million transistors per square millimeter. But there are tons of caveats there, and you can't even take that too literally, unfortunately. So if you were wondering what's going on with process nodes, it is not you, it's definitely them, and it's a very bad marketing term that never should have been invented or used this way. Anyway, so Moore's law. The transistor density has continued and probably will continue. So we will be able to get to 5 nanometer. 3 nanometer also seems technically possible. Not really clear what happens after that. And clearly, this is not my own domain of expertise. But one thing that is very clear is that it is happening with absolutely outsized cost. And what is it worth it to drive to that next node of density? And in that regard, Moore's law is ending. Economically, Moore's law is ending because Moore's law is not about growing transistor density at any price, or it shouldn't be. And economically, we are going to be unable to actually get there. So economically, Moore's law is indisputably slowing down, but there may be a different way of looking at the history of microprocessor development and of transistor development. And for that, I want to turn the Wayback Dial a little bit further back in time. And I want to go to this essay by this guy named Theodore Wright. So this is Factors Affecting the Cost of Airplanes. This is in 1936. So we've now gone back. Actually, it's funny because you've only gone back like 30 years from 1965, but it feels like we're in a different era. And in particular, here is Theodore Wright's graph. And what this is showing is the cost for producing an airplane at versus production quantity. So you've got this on the x-axis here is production quantity, that's log. You've got the cost, that's log, up the side. And what we can see is that as we double the production quantity, the cost drops by a ratio. And it drops by ratio for a variety of reasons. It drops by ratio because of labor. Labor gets more efficient the more you make. It drops because of how you buy material, raw material, and the like material that's already been made by a supplier. All of those things drop as you produce more. And it drops for a bunch of reasons. It drops because of economies of scale. It drops because of know-how. You just get smarter about the way you make this stuff. If I tell you to make something 100,000 times, the way you make the 100,000th is going to look pretty different than the way you made the first one, and you're going to be a lot smarter about it. So this is what Wright observed, and this is what came to be known as Wright's law, that over time, when volume doubled, units costs dropped by 10 to 15%. And the thing that's interesting about this is it's been observed in lots and lots of other technological domains. So Jessica Transick at the Santa Fe Institute wrote a really interesting paper along with some of the folks there looking at Wright's law versus Moore's law in terms of predicting the transistor density and cost, and showing that actually Wright's law is arguably more predictive than Moore's law, which is interesting. Because go back to that original paper by Gordon Moore, transistor cost was a big part of that paper. So interestingly, Wright's law seems to hold, and it seems to be holding now, especially when you look at older process nodes. When you look at those older process nodes, the cost per transistor is continuing to drop. If you've got an M1 laptop, that M1 laptop is on a TSMC 7 nanometer process, and you've got on the order of 100 million transistors per square millimeter on that M1 CPU, on that Apple M1 CPU, and you probably didn't pay that much for it. Those laptops are actually pretty inexpensive, all things considered. And if you graph it out over time, Wright's law does seem to be holding. So that's a really interesting data point. There's a couple of other things here that are interesting just because I found that the paper was really interesting, the Theodore Wright's paper. And he, like Moore, is also thinking about the possibility for new markets to open up as this technology gets cheaper. And one thing that he points out is that we have the usual circle of relationships where price can be reduced most effectively by increasing quantity, but I can't increase quantity until we've had a new market by lowering price. So there is this kind of big circular dependency where as we make aircraft cheaper, new markets open up, more people can fly, more people want to fly, we've got more demand, and we were able to make aircraft cheaper yet again. And that was honestly the dawning of the jet age that would happen between this paper and when Gordon Moore wrote his paper 30 years later. Another kind of interesting foreshadowing is just looking at how this is going to open up this to so many more people as the benefits of flying are more and more realized because of the use of the public airplanes, of surpassing performance and far greater safety. The possibilities of market extension alluded to will be realized. So I think this is really interesting, especially if you think about 1936. Flying in 1936 was very different than flying in, say, 1965. All right, so one final essay, and then I promise we're done with the historical tour, and we will get back to computing and software. So this is an essay. Now we're turning the way back to how we went from 2011 to 1965 to 1936. We are now going to 1865 on the coal question. This is by an economist. And this is an inquiry concerning the progress of the nation and the probable exhaustion of our coal mines. Now, this is, I would say this is like Betteridge's law of headlines if it were phrased as a question, which is to say Betteridge's law of headlines is that if a headline is phrased as a question, no is usually a reasonable answer. But this is 1865. This is long before Betteridge's law of headlines. And this is where Jevons is just showing his hand and saying, hey, by the way, our coal mines are going to be exhausted. So this is W. Stanley Jevons. And Jevons noticed something pretty interesting. What he noticed is that as we being England, became more efficient at using coal, the consumption of coal increased. So it is wholly a confusion of ideas to suppose that the economical use of coal is equivalent to a diminished consumption. The very contrary is the truth. Kind of a strange way to say it. But what he is saying is that as we get more efficient, we are going to use more of it. Now, why is he saying this in italics? Why is he so emphatic about this? Well, let me remind you, he believes that the coal mines are going to be exhausted. So Jevons' whole thrust with this paper, 1865, is that we are going to run out of coal. We, England, are in deep trouble because we're going to run out of coal. And don't come at me about efficiency, because efficiency increases the use of coal. We're going to have more uses of coal, and this is what is known as Jevons paradox. And this is where he restates it again, the very economy of its use, which leads to its extensive consumption. It has been so in the past, and it will be so in the future. I got to remember that line for parenting. I'm not sure that's going to work as well for parenting, but it has been so in the past, and it will be so in the future. Very, very confident, as it turns out. And this is where also Jevons, in talking about Jevons paradox, is also foreshadowing Wright. Wright would be, again, many years later, 80 years later, because again, seeing new markets that would open up as coal became more economically attainable. And in particular, what he sees is steam navigation. Now, keep in mind that while Wright and Moore are both very excited about new things opening up, Jevons is terrified because he believes that a new use of coal is going to accelerate the depletion of coal in England. But what he does see accurately is that steam navigation is around the corner. This is in 1865. There had been at this point steam engines in ships, but it was not really practical. There were a couple of innovations that would come in the next 10 years that would make actually the ocean liner really possible and really transatlantic travel by steam. Of course, the Titanic was steam powered. So this would ultimately not be in vogue until it was replaced by gasoline many years later, or by petroleum. As he points out, sailing vessels would very soon sink into a subordinate rank. So that was a very good prediction. Jevons had some good predictions. He also had some very bad predictions. In particular, Jevons is so concerned that England is going to run out of coal that he will accept no possible explanation for how England will not run out of coal. And in particular, do not talk to him about alternate sources of power. I don't want to hear about wind power or anything else. As all things considered, it is not reasonable to suppose or expect that the power of coal will ever be superseded by anything better. It is naturally the best source of power. And such as air and water and gold and iron are, each for its own purpose, the most useful substances, and as such, will never be superseded. Boy, do not say never like that. This is wrong. This is wrong because of petroleum. So petroleum had been discovered prior to this in 1865, but Jevons felt like, it's not very much of it. There's going to be a lot more coal. There's not a lot of oil. It's like, actually, it turns out there's a whole lot of oil. And this is like the alternate reality that we might have had we not discovered oil. So oil, pretty important as it turns out. Jevons, never say never. Finally, and just to wrap us up on Jevons, I did love this. So Jevons is so terrified that England is going to run out of coal, and he sees technological progress as accelerating England's depletion of coal. That is the Jevons paradox. As we make it cheaper, we consume more of it. As we make it more efficient, we consume more of it. And I just love this because this is from the Google Books, scanned this book. And this, in the copy that they scanned, there's this question mark in the margin. I would love to know what year that question mark is from. I believe it's got to be the 19th century, maybe early 20th century. As my wife pointed out, who's got a PhD in Scandinavian literature, has been in a lot of 19th century literature. She points out it looks like a fountain pen, does not look like a ballpoint pen. But this is Jevons' kind of closing statement of this essay is, so far then, as our wealth and progress depend upon the superior command of coal, we must not only stop, we must go back. To which someone is like, what are you talking about? Like, what are we going to do? Like, not have steam? We're going to go back to sailing ships? I mean, anyway, pretty funny. Why are we talking about this? Why are we talking about Jevons? Why are we talking about Wright? Why more? Well, let's stitch this back to computing, and let's kind of stitch all of these back to computing, and then look at where we're going. So, Andreessen's piece, we overly software-centric, software truisms, but overly software-centric. Moore's law, very prescient, but also slowing. Wright's law seems to be interesting and seems to still be holding for transistors. That is to say, as we make more of them, we are making transistors cheaper. Jevons paradox tells us because I believe the Jevons paradox applies to computing. We've seen it over and over and over again, that people believe, what would we do with more computing? We don't need more computing. The world doesn't need another computer. There's enough room for 6 computers in the world, or whatever the line was from IBM back in the day. But what Jevons paradox has showed us is, as we can do more, we find more to do. And I believe that is going to still hold for computing. What does all of that mean? If you add all of that up, we can expect in the next 20 years a lot more computation in a lot more places. So we are going to see an explosion of computation in many, many, many different places that are not just our traditional CPU. Now, this doesn't just mean, this means IoT. It's like, well, yeah, IoT, sure. Internet of Things, having little moats and so on with CPUs. And yeah, sure, I think that too. But that's not all of what I'm talking about. What I mean is we're going to see CPUs where we once thought of components. So if you take open a machine, there are lots of discrete components in there. And I think a lot of those components are going to have actual modern CPUs. You're going to have 32-bit CPUs. Now, the truth is, there are actually microcontrollers in those components right now. It's just they're generally like 8-bit microcontrollers. I mean, the 8051, the Intel 8051 is, I believe, still the most prolific Intel architecture ever made because it's in so many things. It's in microwave ovens. It's kind of all over the place. Those 8-bit microcontrollers are going to be all replaced in the next 2 decades, if not sooner. And they're going to be replaced with what you and I think of as modern CPUs. An 8-bit microcontroller is not modern by any stretch of the imagination. It wasn't modern when it was first developed in the 70s. A 32-bit CPU is going to feel modern. We can run real software on it. And we can run protective mode software on it. We can run a real operating system on it. And we're already seeing this. We're seeing CPUs in many, many different spots I'm on the server side. If you look at a modern server, we've got CPUs in the NIC, we've got CPUs next to flash, CPUs in the spindle. We're seeing more and more and more CPUs. And this gives us real opportunity. We're going to have all of these compute elements in so many different places that we can now really think and rethink about how we imagine the system. And we can imagine the system as hardware, software, co-design and co-integration. And the good news is, the exciting thing is, that there are lots and lots of other trends that are happening that are accelerating this shift. And this is what I think is really going to come to typify the coming 10, 20 years. So the first is open instruction sets. I mean, people know about x86 and ARM. Those are kind of the two market victors, but they are both really encumbered right now by their history, by licensing, and it makes it hard to put. You can't put an x86 core in kind of arbitrary spots. It's too expensive. It's too proprietary. There are open instruction sets. RISC-V, obviously the Dave Plus-Ultra of that. RISC-V out of Berkeley, Dave Patterson out of Berkeley, developing what is the kind of the modern RISC architecture, trying to learn from all of the ISA mistakes of the past, but making it entirely open, and very importantly, with entirely open implementations. So you can actually get the actual implementation, the RTL, and you can actually synthesize your own ASIC or FPGA with a RISC-V core on it, and you've got your core. So it makes it very easy to add a core to an existing project. That's great. And RISC-V is very promising, but there still remain a lot of gaps to close. And trust me, I would love to be using RISC-V in lots of places that I can't right now because there are gaps to close. There are gaps to close to make software realistic on those things. There are gaps to close to make software realistically debuggable on those things. And we really need RISC-V to focus as much on the SoC, the system on the chip, as the instruction set architecture while remaining entirely open. It's going to be very tempting for RISC-V to walk down the primrose path of proprietary firmware, and it must not. If it does that, it undermines its value. So this is the kind of disaster that x86 led us into with proprietary firmware. We cannot do that with RISC-V. Another big trend that's very exciting is around open FPGAs. So historically, FPGA, the field programmable gate array, actually, when I first moved out to Silicon Valley in 1996, I remember passing a billboard on the highway that was a California license plate as the billboard that said FPGA ASIC. I remember thinking like, wow, what fraction of the population knows what FPGA ASIC stands for? And yet here I am where enough of the fraction knows that you can put it on a billboard. FPGA is a field programmable gate array. This is what allows you to have what's called soft logic, where you can actually you can have effectively software decide what your hardware is doing. Your software is deciding the layout of your gates, and then you are reprogramming the hardware to act differently. And you can dynamically reprogram the hardware. You can reconfigure the hardware. It's amazing magical power to be able to make that kind of hardware dynamically. But historically, it's been entirely proprietary. The bit streams have been entirely proprietary, and you've been entirely dependent upon proprietary tools to generate them. Huge service done by Clara Wolf with the Ice Storm project, and she took the Lattice Ice 40, which is the big FPGA companies are historically Xilinx, now AMD, Altera, now Intel, and kind of Lattice was the third place finisher. And so she took the Ice 40 format, so named because it's a 40 nanometer process, and reverse engineered it completely. And that allowed the open source ecosystem to entirely synthesize an Ice 40 bit stream. And that's really powerful. And the Lattice Ice 40, I mean, it's a really interesting line. We are going to be using an Ice 40 in our Oxide product because it is entirely open. And these things are incredibly small. So the smallest Ice 40, I believe, is just over a square millimeter in size. That's amazing to be able to have that reconfigurable bit of computing be, I mean, the size of a grain of rice, effectively. Is really amazing. So that's very exciting. There are others have followed. A company called QuickLogic. There's actually a great presentation about how they went out to this OR conference, which is around open source hardware, and they realized that like we need to be actually open. We're an FPGA company, FPGA startup. We actually need to be all open. So they've done everything entirely in the open, using Yosis to actually do the verification and so on. A bunch of pointers down here to things to check out: Symbaflow, Verilog routing, Yosis OpenFPGA, and actually just announced, I think, a couple days ago, the Open Source FPGA Foundation. So this is an area that is really exploding, very exciting, and we are going to see, I think, all open FPGAs in the not too distant future, which open up lots and lots of possibilities about how we imagine our future systems. hardware description languages, HDLs. So historically, HDLs have been dominated by Verilog. And if your life has been blessed and you've not had to look at Verilog, your life has been blessed, because Verilog is not such a great programming language. Not really a programming language in any kind of traditional sense. And I mean, it's a programming language done by hardware folks, and God bless them, but it's not great. The later system Verilog tried to kind of clean some of that up. Some people say, like, oh, like Verilog is C and system Verilog is C++. And it's like, yeah, more like Verilog is assembly and system Verilog is an assembler with macros. I mean, it's really, we're still very, very, very low level. The compilers have been historically proprietary, and the languages themselves have been entirely error prone. Anyone that's done any kind of FPGA development for any length of time will tell you this has been really, really painful. We've seen a real explosion in new HDLs, new open HDLs in the last decade. Chisel and MyGen is the BlueSpec, Spinal HDL, Mamba, Pi Metal 3, HardCamel, a bunch of those there. But of these, there's one I want to talk about just for a heartbeat here. So there's something I want to leave you with. It's, boy, this is the best technology that folks have not heard of. BlueSpec is amazing. So BlueSpec is a high-level HDL. Takes its inspiration from formal specification languages and strongly typed languages like Haskell. And BlueSpec's observation is that we should use the expressiveness of the language and move away from the individual wires, which is what Verilog actually has you manage, and move up to a much higher level of abstraction that is going to feel like home base for you and me as software folks, and thinking about the actual like invariance of this module. Like, what are the atomic rules? What are the interfaces? And they've got very rich ways of expressing that. And then the compiler itself puts together these modules and is able to put together these modules in a way that meets all of the invariants. And you get out from underneath some of the really kind of gnarly problems when dealing with individual signals and wires. And really leaning on the compiler. In the words of my Oxide coworker, Aryan, BlueSpec is to system Verilog what Rust is to assembly. So pretty big jump up to BlueSpec. People do not know about BlueSpec, but if there's one thing to go mess around with this after watching this talk, I hope it's BlueSpec. It was proprietary for 20 years. So this is something that has been developed by BlueSpec, the company. It was open source in early 2020. So it is out there. We at Oxide think it is profoundly transformative. We're certainly using it. It is, but I think a lot of us would complain that many technologies get overhyped. BlueSpec is a technology that is getting very, very underhyped. Worth checking out, and I've given you a couple of links to documentation and so on, and then to an Oxide project that actually Aryan has started called Cobalt. That is what we are doing with BlueSpec. So you can see how actually we're going to be using it at Oxide. In terms of the actual software that we use to generate like a PCB, historically that has been a printed circuit board. Historically that has been dominated by proprietary software. That's historically been OrCAD or what have you. Open source alternatives have existed, but they've kind of not held much of a candle to them. What we've seen in the last 5 years is KeyCAD in particular really getting the sponsorship that it needed to become pro grade. So thanks to CERN, Raspberry Pi, and there are a bunch of organizations that have sponsored KeyCAD. And as a result, System 76, KeyCAD is now actual, like you can use it to actually make real boards. And we have at Oxide. So our proto boards we have made using KeyCAD. For our big server boards, we're still using OrCAD and Altium, but boy, the day when we can use KeyCAD feels like it's not that far away. It is definitely software that is worth checking out. And the neat thing is when you've got KeyCAD, you've got these quick turn PCB shops. You can actually go, as we had happen last week, I had an Oxide engineer went from ideation to board sent out for manufacturing in 12 hours. That's pretty amazing. And board is shipping small number of days after that. We'll have that in hand from China, from overseas in what, a week full stop, from end to end. That is pretty amazing. And that kind of iteration on hardware opens doors like that. It is now possible to do things that we could not do before because we can take these quick iterations in hardware. And that is due to not just the quick turn PCB folks, but also to KiCad and the open source there. Just in general, on the board economics, I mean, this is amazing to me. You look at so I've got this. This is my little Nucleo board, Nucleo 144. This is an STM32. This is an H7. This is a 400 megahertz CPU right there. 400 megahertz, a mega flash, a mega RAM, all I/O peripherals. This thing is $30. This is more powerful than the computer that I had on my desktop when I started at Sun Microsystems in 1996. That's bonkers. The fact that you, me, anyone can buy this like pinnacle of human achievement. You can buy for $30 and not just to use as a consumer device, but you've got all the debug headers on this thing and the IO headers. Like you can actually make stuff with this. That's amazing. That's exciting. You look at a BeagleBone Black, which I also called out here. BeagleBone Black, less than $60, a 1 gigahertz CPU, 4 gigs of flash, 512 megs of memory. Way more powerful than my desktop, even like a decade ago. That is amazing. This is exciting stuff, and the economics lowers the barrier to entry. You can also use that BeagleBone Black, by the way, as a logic analyzer. I mean, I got my name brand logic analyzer, my Salier, $400, which is expensive by logic analyzer standards. But boy, when I was a student, when I was an undergraduate, a logic analyzer was $10,000, a $400 logic analyzer. It's just amazing how accessible all this stuff is. We've got open source firmware. So the software that is running at the lowest layers in the stack, increasingly, that's becoming open. The drivers are becoming open. The software at the bottom is becoming open. The firmware for those unseen parts of the system, that's becoming open. It's not all happening at once, but boy, is it happening faster than I thought it would. And it's happening slower in those kind of 7 nanometer SoCs, kind of the Intels and AMDs of the world, but it is happening, and it's amazing. I would not have believed 10 years ago that we were going to see open source firmware, that we would see the ability to have open source. The Intel management engine. Intel's actually contemplating open sourcing aspects of the management engine. Never thought I would see that. So it's amazing. It's a golden age for open source firmware, and it's going to get better. That said, there are still proprietary bits, and even in this little goober, there is a proprietary boot ROM in there. So there are proprietary bits in these things, and the proprietary boot ROMs are problematic. So we really need to move to an all open future where we've got all software, all firmware open. It should go without saying, but the firmware we're generating at Oxide is all going to be open. And finally, another change that I'm very excited about. I know this is probably my apologies for talking about Rust at a Ruby conference, but I'm sure there are plenty of you that have played around with Rust as well. And Rust is really exciting at this layer of the stack, at this bottom layer of the stack. Rust is not only does it make it possible to make fast, correct code, it's code that can be very small. And you couple that with its lack of runtime, and you can fit it anywhere. And you can fit Rust on, this board that I've got runs a de novo Rust operating system that we're developing here at Oxide. We're looking forward to getting that one out there. We'll be open sourcing that in the relatively near future. But it is absolutely clear to me that the future of firmware is emphatically Rust. There is not a reason to write firmware in C at all. To the contrary, now I can't go back to C. I was a C programmer for 25 years, but to be in Rust is to eat the fruit from the tree of knowledge of good and evil. And I now realize that it's unsafe code all along in C. There's so much undefined behavior that you're implicitly relying on. And for firmware, this is really problematic. This is what causes things to just kind of misbehave in the world. And it's very important that we have bedrock in that foundation, and that's going to come from Rust. So very exciting about that development as well. So you add all that up. You add up open FPGAs and open source firmware, and you add up Rust and what's happening with open source instruction architectures, all this stuff. And as my coworker Jess Frizzell tweeted out, hardware is eating the world. So take that, Mark Andreessen. I think hardware is eating the world. And this reply actually to Jess is really interesting. So you may not know who Tom Lyon is. Tom Lyon was Sun Microsystems employee number 8. Tom has been around for a long time. He's done a lot of very interesting things. If you get the chance, you should check out the podcast that Jess, Steve, and I did. Actually, that was just Jess and me with Tom, the Oxide on the Metal podcast. We did an interview with Tom Lyon. Amazing, amazing technologist. But Tom, and one of the things I love about Tom is still just so pure and loves where things are going and always looking forward. And Tom had this really interesting reply to Jess that looking at all of the enthusiast hardware projects, low-end FPGAs, custom PCBs, Pi hats, et cetera, does remind me of the homebrew computing craze of the 70s. That changed everything. This is someone who was bullseye for the homebrew computer craze of the 70s. This is someone who knows exactly what that craze looked like and is telling you, I'm seeing some of the same elements here. As one of my Oxide coworkers said, you know what it reminds me of is when compilers became open source in the 90s. All of a sudden, new kinds of software was possible. That's what we're seeing. It changes everything we can do. We are going into a new golden age. Thanks to Moore's Law, Wright's Law, rise of open source, it is now easier to build hardware than ever before. It has never been easier to build hardware than it is right now. And that's really exciting. And we see this era coming of hardware, software, co-design, hardware, software being designed together. People, software engineers, better understanding hardware, hardware engineers, better understanding software, working together to deliver reliable, secure, high-performing systems. Because that's a real challenge to have all these computing elements and pull them together into a reliable and secure system. It's a huge challenge, but it's an exciting one. We have never had more tools at our disposal. It has never been more accessible to more people. The systems are open. The communities are welcoming. I mean, if you're a little bit tired if you've been in some software communities that have left you a little bit exhausted, come into some of these hardware communities or low-level system software communities, because you know what? The problems are so hard and the technology is so fun that I've found that there's a spirit, an ethos in the community that reminds me of the communities of yore, where people are just excited to build together. So hop on in. Everyone's new to this stuff. People are excited to explain how things work. There are lots of great ways to learn, lots of interesting things to do. Systems are open, communities are welcoming. Let's go build. And with that, thank you very, very much.